Hello, hello. Can anyone hear me? Am I broadcasting? Okay. Okay, awesome. Just to confirm, did you guys have to click on anything in order to be able to hear me, just so everyone is able to join the session? Okay, I guess we can wait just like 1 or 2 minutes until. Oh, okay. Until everyone is able to join. Okay. It seems like people can see and hear me. Okay, I think I can start now. All right. So, hello everyone. Good afternoon if you are in the east side, and good morning if you are in the west side. Um, we are happy that you joined us in this session of the Machine Learning Study Jam. This is the second session about intermediate machine learning. So yeah, I hope you all learn something. I hope we have a good time. And let's go. Oh yeah, I will share the Kaggle link once once we get to the activities. Okay, Vanya shared it for us. Thank you, Vanya. Okay, so this event is hosted by the Google Cloud or Google Developer Group Cloud Edmonton, or GDG Cloud. We are an official chapter of the Google's worldwide network of cloud enthusiasts, developers, data scientists, and engineers. We are led by our founder, Xinli Kai, and our VP, Rohan Saha. And my name is Thales Carvalho. I'm part of the organization team. And I will host and co-instruct the session of the ML Study Jam. For this session, we also have an invited lead instructor, Anirudh. We'll be able to meet him, and I'll present him once he instructs his part of the activities. He will be our ML mastermind that will teach the more advanced activities. Our group is, or the GDG is integrated by over 866 members. We have organized many other events, such as other Python and ML bootcamps. We have hosted Google Technologies events. We had hosted community events, both online and in person. And we have collaborated with multiple local developer groups. So if you want to know more about us, here's the link of our community. And yeah, we hope to see you around. So as we are in Edmonton, we would like to acknowledge that we are based on traditional lands referred to as Treaty 6 territory, a traditional meeting grounds, gathering place, and traveling route to the Cree, Saulteaux, Blackfoot, Métis, Diné, and Nakota Sioux. We acknowledge that all the many First Nations, Métis, and Inuit whose footsteps have marked these lands since time immemorial. So as I have mentioned, we are in Edmonton, and if you are from around the world and you don't know, this is Edmonton. We are located in Alberta, Canada. We are in fact the capital of Alberta. On the right, this is what the city looks like. This is one of our watermarks, the Walterdale Bridge, that connects the downtown region to the southern region of the city. And I would also like to mention that Alberta is home of probably one of the most beautiful national parks of the world in the mountain regions, which in each season can offer like unique experiences. And before we start, I would like to go through our code of conduct. This is a friendly reminder that we want to provide a friendly, safe, and welcome environment for everyone, regardless of gender, sexual orientation, ability, ethnicity, socioeconomic status, and religion. This should be a safe space to ask any question. So please be nice to everyone. We want to learn the most, to get the most of it. So have respect with everyone around, and we should have a good time. All right. So now we go to the contents that will be covered today. So as I said, this is the second session of the ML study jam called Intermediate Machine Learning. And today we'll deal with mostly data processing, some more advanced methods in machine learning, such as pipelines, cross-validation, XGBoost, and data leakage. And this will be mostly a hands-on session. So we'll code along as we learn these topics. And I also invite everyone after this session to try everything out, and in Kaggle you can try this out, try to join the competitions and see how well you're doing in the contents overall. So without further ado, let's go to the introduction. So if you go to the Kaggle link that Vanya shared on the chat, you'll see this page right here. Yes, this session is being recorded. And I see people have some experiences in Edmonton, so that's nice to hear. Okay, so here you'll see all the lessons that we have listed in our outline. So each lesson comes with a tutorial and an exercise session. We're not going to go through much of the tutorial, tutorial sessions today, because we want to have a more hands-on experience. But I'll briefly go through them. And I invite everyone, if you have any questions about them, the tutorials have a very nice overview of each of these contents. So let's start with the introduction. This introduction will review some of the contents that we had that was covered in the last session in Intro to Machine Learning. And this will be a great opportunity to also review features from Kaggle, how the interface works, how to code in it, and how to view our results. So if you click on the lesson, you'll go to the tutorial page where you can see the brief overview. This one doesn't have a lot of text, but the next ones will have a brief explanation of the contents. And here, along with the tutorial, we will also have a tab with data. This type of data is very interesting because you can see the data that we'll be treating during our course. And it has a brief description of all the files and all the data fields that are within the data structure. But we'll go through it once we go to the exercise. So yeah, let's do it. If we click on the link down below, we can start the exercise. And if you click on the exercise link on the overview page, it should bring you here as well. So this is how the notebook looks like. This is a Jupyter notebook. This doesn't depend on your computer to run everything. This is all run in the Kaggle server. And in order to be able to use it, we can click on this Power On button right here. This will start what we call a kernel in Kaggle server, where all these codes that we write here can be executed and we can see the output from them. So this is very friendly to us because we can code from anywhere, regardless of system, or prerequisites, or anything. This is always ready in your browser. So in the right-hand side, we can see that data that we just saw in the previous web page. Here in the input session, we see all of those files that was listed before, and we can open them and see how they look like. So let's say we want to open train.csv. We'll see a lot of rows and columns here that are related to our data set. So let's first take a look at what this data set is about. So let's go through the actual notebook to see it. Okay, so our session is now started. We can run our code and they will be executed. So let's start with the setup block. So yeah, firstly, let's talk about what is a code block in a notebook. A notebook is composed of both text and code, and we can split them by blocks. So all of these are text blocks. These are text blocks. They don't do anything in practice. They just serve to guide us. And what is going to run in the kernel are these code blocks, and we can run them individually by selecting them, clicking on them, and then clicking on this play button right here. This will run all the lines in here and will show the output of the code cell. For this specific cell, we don't have to worry about what it's doing, because this is only a setup code for using Kaggle and checking and loading the data and checking if your results are correct. So don't worry about what this setup block is doing, but we'll go through the next blocks. All right, so now we'll start talking about our data. So this is data from a competition, a very famous competition actually from Kaggle, called housing prices competitions. So in this data set, our goal is to predict the price of a house based on many features that it may have. So along these features, we have the total area of the house, how many rooms does it have, how many floors does it have, the year of construction, and so on. And we want to see if we can make a model that will properly predict the house price based on these features. So if we expand our data section here, we'll see exactly those features in our columns. So we have this ID column, which is just to identify each row of our data set. We have many numerical data here, such as the area of the house. We have some categorical columns as well, such as the street, the alley, and we'll learn how to deal with them in this session, because our models usually only deal with plain numerical data. But what should we do when we have an invalid number in the middle of our column, and how do we deal at all with these categorical data? So that's what we'll see today. All right, so in this first code cell, we will load our data, and for that we'll use pandas to deal to create our data table inside in our memory. Pandas has some very handy methods to read the dataset. So our dataset is all in CSV format, and Pandas has a straightforward function to read a CSV file. So we can simply read the train dataset and the test dataset into variables in our memory. And if you're unsure how these methods work, Kaggle has a feature where if you hover your mouse over the function and hold Control, you can see, well, this might not be as helpful, but you can see what is the documentation of the function like. So maybe if you do it for the sklearn functions, you'll have a better guide on how the function works. But if this is not enough, always look around on how these functions work. So in this case, Google is your friend. Don't be afraid to Google what is read CSV, what is train test split, and so on. So what these lines are doing is reading both the train and test.csv and loading to xfull and xtestfull. And we are indexing the rows by the column named ID, which is that first column that we saw in the CSV. And now we are going to separate what is our prediction to our features. So we want to predict the sale price. There is a column named sale price. So as now Xfull is a pandas dataset or a pandas data frame, we can get that column by just selecting it as an attribute. So we will also get some specific features out of our dataset. So in this case, we'll only take a look at these features. In the later sessions, we will use more and more features as we learn how to deal with them. But for now, we're only loading these numerical columns. And lastly, we are going to split our dataset in training and validation sets. So we do this because we always want to verify whether our model learned in the training set is able to predict correctly a validation set without having that validation set as part of the training. And this is very important when your test data set doesn't have your prediction, because you can't properly validate whether that is whether your method is working. But with a validation data set, as it has the prediction column, you can validate. And in fact, that's why it's called the validation set. Here in the tutorial, there are some handy links for all of these concepts, such as validation, what are features and prediction targets. So if you're unsure about them, please click on these links and take a look at the short tutorials that they are recommending. All right, so we can execute the code. As I said, we can execute a code by clicking on this button. We can also execute by pressing Control-Enter, just to make it quicker. And now we have another code block that calls the head function in our data frame. This is just to check what are the first few samples of our set. And we can see that our set is composed of exactly those numerical columns that we selected here and the ID column. We also don't have the sales price anymore because that's separated into a separate variable. So in this case, it would be Y train. All right, so let's start by checking how some models will perform in this data. So in the first session of the ML Study Jam, we studied what are random forest regressors. So we're gonna use them here. And if you want to review them, there's a link to it as well. But we're just for now we're just gonna say that they're models that work well, and we'll deal with the data to check how dealing with the data impacts the performance of our model. So for this session, or for the introduction, we'll just define some 5 different models, and there will also be a function named score model, which will take a model, fit in our training dataset, and predict using our validation dataset. And this score model will return the mean absolute error of our predictions compared to what are the true values of the validation set. And this will give us a score to our model. In specific, this is the mean absolute error score. And again, if you have any questions about that, there's another link to what is a mean absolute error. but it's just important to know that it provides a score to that to our model, and we want to minimize that score. So we have a model that has a lower score. That model is considered better. Okay, so let's run this this code. It will print the score model for each of the models that we defined before here, and we see different numbers for each model. And if we want to just select which is the best model out of these 5, what we have to do is just look at the one with the lowest mean absolute error. So in this case, it would be model 3, which has 23,500 as the mean absolute error. So in fact, this is the first question of our exercise. We have to say what is the best model. So here, each of the models is defining these variables. So we can just write model 3 here. And then we can run this code, and Kaggle will check whether our answer is correct. And if it is, it will show a green text saying correct. And if you, oh yeah, Kaggle always, Kaggle always has this handy code block here with hints and the solution to the problem. So if you ever feel confused on how to answer the question, you can uncomment, let's say, the hint here, execute this this code, and then it will give you a hint on how to answer the question. And then if still you're unsure on how to answer, you can uncomment the solution, and it will give you it will propose you a solution that works in the code above. But I encourage everyone to always try to answer on your own before before going to this, because, well, that's how you learn, right? You should search around, go through the documentations, go back to the codes, go back to the tutorial, and see how you should answer the questions. Right, so let's run this again to clear the output. And okay, let's go to step 2 now. Now we're gonna learn how to generate the predictions in the test dataset. So in this case, we don't have the prediction targets. We'll only be able to predict them and have the sales price numbers that we think are correct. And the only way that in Kaggle we can check our results is if we enter the Kaggle competition and submit our test results. So because it's like, let's say, more difficult process, we can't properly use the test error to validate our model. So that's why we're only doing this at the very end, so we can submit this to the competition later. So here in the tutorial, we're just gonna define let's say, generic random forest or default random forest model. So if we start typing here and press tab, our notebook will show the class that has been loaded before. So we can just click on it. It will type out the random forest progressor for us. And again, if we hold control here, it will show what this class does. But this is the same class that we were dealing before, so we can just declare it here and use the default parameters, which is what the exercise expects. All right, so now the introduction is teaching us how to generate the test prediction. So we will first feed our model to our training and validation dataset. This line is just an example of how we're doing it. Later on, we'll do a lot more than just this. But after, let's say, we have properly trained our model, after that, we will predict our sales price in the X test, and we'll save that in creds test, this other variable. And in order to save the output as a file, we will just get the index and sales price from that variable. We'll save it in a data frame, pandas data frame like this, and then we can use the function toCSV from pandas to save it like this. So if you run this, you'll see that apparently nothing happened, but this saved this submission.csv file, and you can see it in here. So if you open this output folder here, you'll see the submission.csv, and this has pretty much this data frame that we load. So you can download this file, and if you do so, you will see something like this. So this is a CSV file, so every component is separated by a comma. You have all the IDs and all the prices on the right, and this is what we will submit for the competition. And here in the tutorial, there is a guide on how to do it. If we have time today, we can go through how this is done, but we invite everyone to do it because it is probably the funniest way of learning how to do ML. We're trying to get as much score as you can, trying to get a high place in the rankings and tuning your model along the way. Okay, we hope that with the tutorial today, you can get a very nice score in the competition. Yeah, let's go through that. All right, so let's start with the proper content. The first class is about missing values. This is a problem that happens a lot in machine learning, where sometimes a row in your data set simply doesn't have a value for a specific column. And we learn how to deal with that in this class. So here in the tutorial, there are 3 standard approaches on how to deal with these missing values, and it explains them in a very broad way. So our first option is to simply drop the column that has any missing value. So let's say here that this bad column has not a number cell, and we simply ignore that in our model. This is one option. But we are probably losing a lot of information here, so we might be able to do better. So a second option is to do imputation. So instead of dropping this whole column, we will input fake values in these not a number cells. So in this case, we are inputting the mean of the column. So we go through all the values and calculate the mean of them, and we suppose that these not a numbers could be that mean. And then we have a third approach, which we do the same imputation as we did before, but we also flag the rows that have been imputed. So this is a way of telling the model that, okay, maybe these values not too trustable, but I'm giving you something just for reference. All right, so the tutorial goes through an example. We're not going to go through it today because we're going to see this in practice. So let's go ahead to the exercise. All right, so let's turn on the kernel again, and we'll see the same data set that we had before. This will be a running example of our whole session. So every time we'll see the same data set. And once again, we'll run this setup cold cell once our session has started. We don't have to worry about that. This is just to make sure that Kaggle works. Okay, so a question from the chat: isn't dropping the row also an option? Yes, that's a very good point, and it really depends on your data set. If there are like problematic rows with a lot of not numbers, it might be a good idea to drop the rows. And there are many other approaches to missing values. These are just 3 examples, and as you pointed out, there are many other that could be used for specific cases in your data. All right. So now that our setup is done, we'll once again load the data set. In this case, we are only dealing with numerical data. So we are dropping all the columns that are not numerical with this function. And so this will give us more columns that we had before, but this will be what we're dealing with now. Okay, so we have another question in the chat. This is a supervised machine learning, supervised model. Which is better, unsupervised versus supervised versus reinforcement? So there is no better approach. It always depends on what data you have. So if you have labeled data, you're dealing with supervised learning. If you have unlabeled data, you're dealing with unsupervised learning. And if you're dealing with getting rewards in an environment, then you're dealing with reinforcement learning. So for these sessions, we assume that our data is labeled. So we can always predict and check the error of our prediction. So this is all dealing with supervised learning. All right, so let's run this cold cell to load our data set in our variables again. And if we check the header of our X string, we'll see a bunch of numerical data again. And with a first glance, we can already see the problem. So there's another number here, and there might be other not numbers along the way. So we have to deal with them now. If we just run a regressor with this data, there will be errors because they're non-numerical data. So we have to deal with them before passing the data to our models. So let's start by investigating the problem that we're dealing with. So let's run this data cell that the notebook gave us. So what this is doing is firstly printing the shape of our training data. So with this attribute, we see how many rows and how many columns our set has. And now we're running this function to count how many null values we have along the column. And then what we're printing here is each column that has more than 0 or any number of missing values. So all columns will have 0 unless they have missing values in them. So that's what we're printing here. So with this, we can see that our set has 1,168 rows and 36 columns. And out of these 36 columns, the column lot frontage has 212 missing rows. The area has, this area column has 6 missing rows, and this garage year built has 58 missing rows. So we have to deal with these in order to move on. All right, so there's a little questionnaire about these this data that we see. So these are simple questions about this output. So yeah, how many rows do we have in the training data set? I invite you guys to answer it. Let me scroll up a little. So what we're doing. So for the number of rows, this is very straightforward. This first print statement, yes, correct. As was stated in the chat, this first print statement prints the shape of our dataset, and this first number is the number of rows. So this is what we're writing down here. All right. So for how many columns in the trial data have missing values, we okay, so what should we write down here now? So for this, we have to simply count how many columns this last print statement printed, because this is already filtering out every column that does not have a missing value. Yes, that's correct. So we have 3 columns here, so there are 3 columns with missing values. And now, how many missing entries are contained in all of the training data? So what should we write down here? So our print statement also has the information to answer this question. We simply have to add these numbers together. And yes, 276 is the answer. We can also write down the sum explicitly like this. But yeah, that's 276. All right, so let's run this cell to check if this is correct. And indeed it is. Okay, so this is the issue that we're dealing with. We have 3 columns with missing data out of the 36 columns. And in them, we have 276 missing entries. So let's see how we should deal with them. And yeah, out of those three approaches that we saw, what do you guys think is the best approach to deal with these values? So think about how many rows we have in the whole data set versus how many missing entries that we have here. Is this a big number? Is it okay to drop the columns that have these missing entries, or are we losing too much information with this? What do you guys think? Correct. So as we have a lot of rows in our data, and there are relatively not many missing entries, we would lose too much information if we simply drop those columns. So we can already see that dropping will not be a good option. So we'll have to do some kind of imputation. So here in Kaggle, after this discussion, we can just run this code to receive the credit, and it will state exactly that we said. Dropping the columns is unlikely to yield good results. All right, so now we're going to define a way to score our data processing, and to do that, we define a somewhat default random forest regressor, which will be run in our adapted x train, x valid, and y train and y valid, and we'll print the mean and absolute error of the model in this data. So in the case of this class, we're not worried about the model. It will be fixed in every time we run the score data set, and we're only worried about transforming this data in order to help our model to learn. So let's just run this code cell in order to load score data set to our memory. And yeah, let's go to our first approach. So we already know this is not going to be very good, but let's try dropping the columns and see what score do we get in our score dataset function. So the first step here is to get the names of columns with missing values. So let's try to code along here and see if we can do it. So how should we get these names? Let me write a structure here just to aid you guys, but I would like you guys to go with me in the code and see if we can write this code together to drop the columns in the data. So firstly, we can get the name of all columns with the columns property. So let's do xtrain.columns. This will give this will give us all the columns in our data set, and we can also define a list of the columns that we want to drop. So let's define an empty list like this, and in the end, this should be a subset of these columns that has missing entries in them. So yeah, how should we fill this list right here? You can also try to just explain how you would do it without like writing the function itself, because here we're going to need to call some function from pandas to get whether the entries are null or not. So yeah, if you just write out the logic, I can translate it to code here. Yes, so this is at the end of this part right here that we're going to write. This list will have the names of the columns with missing entries. So we don't really want to simply copy these here. We want a more systematic way of doing this, but it will be quite similar to what was executed here before. So in order to fill this list, we'll have to go through all the columns in our all columns list. So we can write a for loop here for column in all columns. So this will iterate through every column name that we have here. And now we have to check whether that column has any missing entry. So we can do that with an if statement. So we can write down if our dataset xstring in that column has any null value. So the function is null will return true for each entry if they have if they are null or not, and we can and we can check if there was any true value here with the function any. So this will return true if the column has any null value and false or otherwise. So if it does return true, what we do is simply append to our columns to drop the column the column name. So this in the end will have a list of all the columns we have to drop afterwards. So now we can simply drop those columns, and pandas has a handy function to do that. So we just have to call xstring.drop, and we can use the list that we just defined, and we have to also specify which axis we have to drop in. So as we're dropping columns, this is the axis number 1. If it was rows, which is the default behavior, it would be axis number 0. Yes, so that's a good point that Vanya shared in the chat. These are some very basic approaches to how to deal with missing data. And we have many other approaches that kind of built on top of these concepts. But we're going through the basics for now in order to get familiar with these steps, right? Okay, so let's check if what we did is correct. And yes, okay, it's correct. And okay, now we'll check what score we got by doing this approach. So we got 70,800 as the mean absolute error. So remember that this is using a predefined model, and we're just passing these reduced, train, and valid tables that we just processed before. And so this curve tells us like how good this data processing is. So now we'll compare this to imputation, which as I described before, this is inputting fake values into our missing entries in order to give some information to the model. So to do this, the sklearn the sklearn class library has a class called simple inputter, which will be very handy to us in order to input data. We don't have to worry about the logic of like calculating the mean or the median in order to fill in these values and then searching where is the missing the missing values, because sklearn can do it for us. And this is often the case with these ML frameworks. We don't have to worry about the inner pieces of the logic. We can call these more generic functions in order to do this job for us. We just have to worry about the higher level behavior of everything. Okay, so let's use this simple inputter class. So again, if we hover our mouse over the class and hold Control, we'll see the documentation of the function, and it will describe all the parameters and attributes that it has, and it will also show a simple example. So for now, we'll just use it with its default parameters. And yeah, let's see. Yeah, let's do it. Oh, yes, that's a very good point in the chat. There's a question about if there's an imputation other than mean or most frequent, which is the median of our data, like looking at the relationship and correlation between columns. Yes, that's a very good point. When you go through missing data, you will have to go through a lot of data science around our data set, and if you find some correlations between other columns, you can definitely get a better estimate of what your missing value should be. So maybe you can even have a model to predict that value. There are many options of what you could do here. But then again, we're just taking a look at the basic options, basic approaches that we can do for now. Okay, so let's declare our imputer as my imputer, and this will call the class with the default values. Then again, we can play around with these parameters that the class offers to us. But for now, we're just using the default behavior and see what we get. So in order to use the imputer, and this is often the case with the sklearn classes, we have to first fit the imputer to our training data set. So one way of doing this is calling my computer.fit. And let's see if, okay. If we go to the documentation here in the example, it simply calls this function into a given data set. And what we're doing, what we're going to do is fit it to the training data set, which is what we assume we have the full information of. And this will basically calculate either the mean or the median or whatever strategy we're doing with the training data set. And then when we call transform, it will apply that strategy to the missing values. So let's call myImputer.fit in xtrain. And our imputed xtrain will be myImputer.transform. So at this point, our imputer is fit to our training data set. So it already knows what are the what values we should fill the null entries with. And the imputed xtrain will be a transformation of xtrain. And same will happen to xvalid. So we'll have a myImputer.transform in xvalid. And right here, this is just to get back the column names, because the sklearn method doesn't keep the column name, so we're just gonna get it back from our data set. So the imputed xtrain columns will be the same as the xtrain columns, and same for the xvalid columns. All right, so let's run this. Oh, whoops. Oh, okay. We also have to, I forgot to read the exercise, and we have to create a data frame with this transformed data here. So what we have to do is simply wrap this transform call into pd.dataframe. Yeah, whoopsie. So let's do this here and here. And okay, now it works. All right, so now that we have the inputted data, let's check what the score that we have. Yes, that's a good point. This is not always trivial, but you have to know how to interpret the error message that you get from executing the code, and by learning how the classes work and how and what the error is telling, we can have an idea on where the error is, and we can start on fixing it through there. But I can already tell you it's not easy at first. You'll always have to search somewhere else in order to get to know what problem you're dealing with. But this is very, very helpful, like being able to read the debug message or error message. All right, so now we see that we have a different error. So let's compare it to what we had before. So we see that this has a lower error than what we got here. And why is that? Did it surprise Anyone? Why do you think that the approach here had a lower error than the error here? Maybe just to help us answer this, I can also run the hint function. Yeah, what was our assumption about the two methods? Like, we thought that imputation should give us better result because the missing entries were relatively was a relatively small number in comparison to the other entries, but we got a worse error. Yes, insufficient data could be one explanation. There are many other possible explanations, and if we run this check here, it will give us a very complete explanation of what the reasons could be, and but this is mostly to tell us that these hypotheses are not, or not even hypotheses, these assumptions about what would do better, they are not always correct. We have to really test many different approaches to dealing with our data, many different approaches to tuning our method, trying out different models. And we'll most of the times we'll just be able to tell which one is better by running them. There's no simple answer. So yeah. So in this case, one of the explanations might be how we were feeling the inputted data here. So we were using the default strategy here, which is the mean value of our data. Maybe if we use either median or most frequent or some constant, maybe a high constant, the models could perform better. But then again, this is a matter of trying out these methods and see what does better. All right. So yeah, we're not going to go through dealing with these attributes now, but I invite you guys to try out these methods and see which one works better with our data. But let's use any approach here to get our pre-processed data. So let's create another imputer in the same way that we had the imputer before. So this will be a simple imputer strategy. I'll just define a different strategy now just to see whether it gives us a different result. So let's do median, which is a very standard approach for an imputer. And for our transformed data, we'll have to wrap around the data frame. Let's not forget that. And then we can call the imputer. There's a handy function here that calls both the fit and the transform functions at the same time. So we don't have to do one line for fit and one line for transform. We can do them together like this. And we're transforming the X string data. And we'll do the same for valid. Imputer.transform. So we just fit our transformer, our imputer with the training data set, and we're just applying what we learned to the validation data set. and this will be transformation of x valid. And now this will and now we'll just check how our final imputer here performs in our model. This is just defining a model again, but this will be used to generate the submission file. And we can see that we performed better than before. Let's check. Yeah, we performed a little better now. So maybe this was one of the reasons that we performed worse by inputting the mean with our simple imputer. Okay, that's pretty good. Maybe we can use this to submit our to submit in the competition. So let's run the X test now. So we'll have to do the same pre-processing function that we did in our training dataset to our test dataset. So this will be, once again, pd.dataframe, imputer.transform, but now in X test. And our predictions will be the predictions of the model. So we'll run model.predict on the final X test that we just declared there. All right. So with this, we can save these results that we got here into a CSV file again. And once again, this file is available here. And this is hopefully a better submission than what we had in the introduction. So yeah, let's keep working on that. All right, so this is it for missing values. Next up, we have categorical variables. So yeah, please ask any question that you may have along the way, and but otherwise I will continue with the contents here. All right, so categorical variables. So categorical variables are a special type of data that only has a fixed number of possible values. So this could be, let's say, a number of stars of rating in a product. So the categories would be 0 star, 1 star, all the way up to 5 stars. We only have 6 possibilities, so it would be a variable of 6 categories. Could also be a yes or no question, so the categories would be yes or no, and so on. And these often represents a large portion of our data. So we have to process them somehow in order to learn something from them. But we can't use them straight away because our model only expects numerical data. So we have to somehow transform our variable into a numerical variable. So the course here suggests 3 approaches. The first approach is to simply drop the categorical variables. So the same way that we did before, we'll just check whether the column has a categorical variable, and we'll drop that from the data and see how the model performs. The second approach is to do an ordinal encoding of our data. So we'll assign a number to each of the categories, and we assume that there's an order in these numbers. So in this case, never is 0, rarely is 1, most days is 2, and every day is 3. And this order will be important to our model. So this is why this is called ordinal encoding. But if our categories don't have some kind of ordinal meaning, so let's say this is a color category, like we can say that red is 0, yellow is 1, and green is 2, because there's nothing telling us that yellow is somehow 1 greater than red, or green is twice as many as yellow. So we have to do something different with this data. So there's an approach called one-hot encoding. So we split this single categorical variable into as many categories do we have, and in these columns we'll have either 1 or 0. So there will be 1 if the original column had that category, and 0 otherwise. So it will be a table mostly of zeros, except on the columns that the original column, or except in the columns that represent the original category. So yeah, let's see how all of these approaches work in our exercise. All right, so let's turn on our cell. We can see one way of turning on the cell is simply running it here, running the setup block here. So it sets up our environment and turns on the Jupyter notebook. So yeah, this is once again the setup block. We don't have to worry about it. And now we are reading the data. Once again, we are loading our training data set into X, and then splitting that into X train, X valid, Y train, and Y valid. In this class, we're not going to deal with the missing values, so our approach here is just to drop those columns. But of course, you could do the approaches that we had before. And yeah, here we are separating the prediction from the features. All right, so let's run this to have our data in memory, and let's check the header of our data set. And here we can see that there are a lot of categorical columns. Like all of these are categorical. So there's a lot of data here. We want to make use of them. So let's see how the different approaches do with these data. Once again, we'll define a default regressor here in order to evaluate our data processing. So this is the same function as we had before, score dataset. So let's just run it to load this function in memory. So let's start with the first possible approach, which is simply dropping the columns that have non-numerical data. So in order to do that, there's a very handy function from pandas. We can simply call xtrain.select data types, and we'll select all of the data types except a data type called object. So this is kind of let's say arbitrary or abstract data type of pandas that simply tells us, oh, I couldn't parse this data into either a real number or an integer number or a Boolean value. So I'm just calling it object. So texts are going to be called as objects in our set. So for the first approach, we'll just exclude them and see how our model scores. So let's do that with the valid dataset as well. Exclude object. And let's run this. And let's see what is the score that we get with this approach. So this is the same score that we had in the first step before. So that's 17,800 mean absolute error. All right. So now we'll go into the other approaches. But before trying to parse the categorical variables into ordinal or one-hot encoding representations, let's see what we're dealing with. So let's take a look at one of the categorical columns called condition 2. And we'll take a look at what values do we have for this column in xstring and in xvalid. So this unique function simply filters out what are the unique values that we have in each data set. So we have basically a list of all the categories that we see along the data set. So if we run this, we'll see all the categories that condition 2 can be. But we see a problem here. This is the list of categories present in the training data, and this is the list of categories in the validation data. If we simply run our encoders with this list from the training data, there will be some categories from the validation data that won't have any encoding value. So that's something extra that we have to deal with. There could be missing categories from our validation and test data set that we haven't seen in our trained data set. And we can't just assume that we can give them an extra column in our encoding because we don't know that they exist. We supposedly only have information about our training set. Okay, so we're gonna have to deal with that. Just keeping it in mind, but let's see. And in fact, this is the first question. I kind of gave away the answer with this discussion, but so it is asking us if we simply write an ordinal encoding to fit our data, we would get an error. And this error would be because of these missing categories from the validation set. They wouldn't be encoded at all. The system would give us an error. So if we run this code, this is exactly what the output says. All right. So in our case, what we're gonna do is, if we encounter these what we call problematic columns that have like different categories in training and validation set, for now we're just gonna drop them from the data set. And of course, we could deal with them with a number of different ways. We could possibly replace the unknown categories by some default category. That is another very common approach. We could maybe impute data with a most frequent or a mean imputer to those problematic entries as well. But we're doing a simple approach here, which is drop these problematic columns. All right, so this solution here or this code here already does that for us. We're lucky that we only have 3 problematic columns. So these are the columns that have different sets of categories in training and validation set. So we're dropping them from the dataset, or we're gonna drop them from the dataset. All right. So now we're ready to apply the ordinal encoder to our dataset. So the notebook already provided us with the code that drops the problematic columns for us, and we just have to apply the ordinal encoder to the set. So in order to do that, we will use these variables that were already defined. So let's copy these, and we'll only modify the categorical columns that we found here. So these are what they called good label columns that can be safely ordinal encoded. So let's filter out those columns. So what was the name again? Good label columns. And we will apply the ordinal encoder to this set. So let's first define what our encoder is. So let's call it just ordinal encoder, and it will be the ordinal encoder class with the default parameters. Of course, we could check how it does here, like how we could sort the categories, but let's just use the default values for now. And once again, we're gonna use this encoder in the same way that we used the inputter in the last session. We're gonna call it fit transform method, which will take a look at our data. So we'll pass X string here, but as we are filtering out only the or as we're filtering only the categorical columns here, we also have to filter the same columns that we should see here. So we're now our encoder has learned the order of our categories with fit and has already transformed our X string with transform. So now we'll just have to transform X valid as well. So we're going to do the same. This will be ordinal encoder dot transform in X valid in good label columns. All right, let's check what we did is correct. Yay. And okay, let's see how does this approach compare to what we had before. You could already see that it took a little longer for the score dataset function to run, and this is because we have way more columns now, and we can see that we got an improvement. So if we just dropped the categorical variables, we had 17,800 as the mean absolute error, but now we brought it down to 17,100 approximately. So this is good. So the categorical variables have some meaningful data for us. All right. So so now the notebook is only asking us to run this code, and let's take a look at what it's doing. So So now we're going to see how many categories we have in each column. And this will give us a better understanding of our data. So what this is doing here is traversing all the X-string columns here and counting how many unique values we have along the way. And this function here, or this wrapper here, is putting everything to a list, and then we are sorting that list by the second entry, which is the number of unique values with, or unique categories within a column. So we see that most of them have relatively few categories, but some of them have a lot of categories. So this is what we call the cardinality of a categorical variable. So we have some questions about cardinality here. So let's go through them. First question is, how many categorical variables in the training data have cardinality greater than 10? So yeah, what do you guys think? Looking at this list, how many do we have? So as the category is simply the number of unique values in each column, and this print statement is telling us how many unique values we have in each column, we just have to check how many columns have more than 10 unique values. And as you guys said, we have 3 of them. Perfect. Okay. So now another question. How many columns are needed to one-hot encode the neighborhood variable in the training data? So let's go to the neighborhood data. And the neighborhood data has 25 entries. So how many one-hot columns do we have to declare in order to do the one-hot encoding of neighborhood? What do you guys think? Okay, so this is a very interesting answer. 24 is technically correct because we can, as one of the columns will always be the composition of the rest of the data, we can simply drop one of the one-hot encoding columns, but if we're just following the definition of one-hot encoding, we're going to have 25 columns. But 24 is also a technically correct answer. It's just, let's say, more advanced than we are right now. So let's just say 25 here and check our answers. Okay. So let's reason on how these number of cardinality will impact our encoder and how our model learns from the data. So firstly, let's suppose this case right here. Consider a data set with 10,000 rows containing one category column with 100 unique entries. So if we replace this column with the corresponding one-hot encoded, how many entries are added to the data set? So here we're talking about entries and not columns. So the entries here could be thought of the cells in the data set. So how much data do you think that we're adding to our data set? How many entries are we adding if we replace only this column by its one-hot encoding equivalent? So in order to calculate this, we can think of how many columns how many columns we will have at the end of our one-hot encoding. So at the beginning, we have only one column, which is this categorical column that we're dealing with, and 10,000 rows. So what we have at the start is 10,000. So how many we are adding will be something minus 10,000, which is the original number of entries. And at the end of our one-hot encoding, we will replace this one categorical column by 100 columns, and each one will be the one-hot encoding of that category. So at the end, we'll have 100 times 10,000. So we can simply write that down, or we can do the math here. This will be 1 million minus 10,000. So this will be 990,000. So that's the number of entries that we'll get by replacing the one-hot encoding. And if instead we replace the column by an ordinal encoding, how many entries are we adding? What do you guys think? So as the ordinal encoding does not add any column to our data set, we are simply replacing the categorical column by a numerical one. We're not adding any column here. So the answer here is 0. Let's check. Correct. Okay, so as we add a lot of columns if we do one-hot encoding with categorical variables with a high cardinality, here we're just going to drop these columns here because they would add a lot of computation to our model, and maybe it could get like kind of confused with how many data it sees, like how many columns it sees. So to simplify things, we're going to drop these high cardinality columns. Then again, this is one of the possible approaches that you could do with this case. Many other are possible, but here we're going to take in a simple one, which is dropping these columns. So this cell here is filtering out the ones that have cardinality less than 10, which are the ones that we're going to use. And we'll list all the columns with high cardinality in this list here, which will be dropped from the data set. And the rest of them will be one-hot encoded. So that's how we're going to deal with the data in step 4. All right. So in order to encode our data, the notebook already says here that we can use as many lines of code as we need. And we're going to use these one-hot encoder class from sklearn. So let's declare our encoder. We'll call it OH encoder, close one-hot encoder. So let's use it as is for now, and let's filter out what are the columns that let's get the columns that will be used for our one-hot encoder. So if we run OH encoder to our X string, this is basically how we would transform our training data set, but we have to do something extra here, because this has not only categorical variables, but it has also numerical ones. So let's just filter the ones with low cardinality. I gotta do this again, I'm sorry. So this is fitting and transforming the categorical variables that we are interested on. So let's save these variables into OH string. And before I forget it, let's wrap this into a data frame. All right. And this is creating the columns for the training data set. We'll do the same for the validation data set. So I'll just copy this, but now we will just transform instead of fit transform, and we'll deal with the validation data set. Okay. Now, once again, we have to restore the columns or the indices of the dataset, because the one-hot encoder dropped them. But we can simply restore them by saying that the index of the data is the same as the X string index, and we can do the same. Oops. And we can do the same. Oh my God, sorry about that. We can do the same for the validation data set. So this will be equal to the xvalid.index. All right. Okay, so this created our one-hot encoded, or these created our one-hot encoded columns, but we still have to drop the original categorical columns. So in order to do that, we'll declare another variable called the numerical dataset. So this is just the original dataset, but with the object or the text variables dropped. So we will run xstring.drop, and they already gave us this variable that has all the object columns. And we are dropping x is 1, which is the column. And we'll do the same for x valid. All right. Now we have the one-hot encoded columns and the numerical columns, and we just have to join them together. So we can use OH, or we have the line here. We can simply do pd.concat. This is a function from pandas that concatenates different data frames. So we have to concatenate the numerical dataset with the one-hot encoded dataset. So simply do numerical X string with OH calls string. And we are concatenating over columns. So we have to specify axis as 1. And we're going to do the same for valid. So here we are concatenating the numerical validation dataset with the one hot encoded validation dataset. And just one another thing to make the code to ensure that it runs correctly. Let's just make sure that the columns are correctly labeled as strings, because when we create the one hot encoded columns here, maybe it will be given a name that is not in a string format, but we want to read them as strings later. So let's just make sure that they are correctly identified. So let's go through the columns and we'll say that they are, let's just transform them into strings. So they will be themselves, but as type string. Oops, I don't need comma here or quotes here. And we're going to do the same for the X valid. All right, so this should give us the one hot encoding of our data. Let's run. Hope it's correct. Whoops, what did I do? Okay, so there's an error in line 6. Let's check what is going on here. What is the error message? Found unknown. Oh, okay. We forgot to drop the categories that we identified before. Luckily, the sklearn one hot encoder has can do that for us. So it has a property called handle unknown. And if we go through the documentation here, it will give us all the possible ways to handle unknown categories. And what happened was it just gave us an error when that happened, but we want to simply ignore that. So the resulting in that case, the resulting category will be all zeros for that category. Okay, so let's do that. Ignore and run again. Still need to encode some of the category columns in your training data. Let me just take another look here. Oh, okay. I think this is because of the sparsity. Check. Okay. All right. So this is just to ensure that. Let me go to the documentation here. So the sparse the sparse method here will return us a sparse matrix, which is better to handle as in a model, but it's a little bit more complicated than what we're dealing today. So we're just disabling that for now. So, okay, by running it like this, we got correct, and we can check what is the score that we get with the one hot encoding. And surprise, we got a worse score than doing an ordinal encoding. So once again, we will only be able to know what is the result of these data processing once we run them. And although one hot encoded is generally better, applying that as is with these procedures resulted in a worse score than the ordinal encoding. This could be due to a number of reasons. One of them could be that the model might not be good with a large amount of columns. It could maybe a different model would do better with them. Maybe these data that we are encoding as ordinal encoder, in fact, has some ordinal property, so the model is able to learn that. And yeah, we have to test and see what gives us the best result. So now again, we will have another section to generate our test predictions, and this would be the same procedure as we did before to generate that submission.csv file. I'm not going to do this again, as we're going to explore other stuff in the next sessions. So yeah, this is it for the first 3 classes of the intermediate machine learning, and our lead instructor Anirudh will cover the next notebooks. So before I pass the word to Anirudh, I would like to inform everyone that at the end of this session we will have a raffle. So if you stick to the end of the session and fill out the ending survey, you will, and also RSVP to the next session, you'll be able to enter a raffle to win a Chromecast Mini. Unfortunately, this is only available to Canadian residents because this is a physical product and we're only able to send it to Canadian residents. But yeah, stick to the end in order to get to enter the raffle. And can also take a little break while Anirudh comes in. And in the meantime, I will share. Oh, Vanya shared the survey link. Thank you so much.
Yeah, so before we begin, we'll just take a break for 5 minutes. It's 1:53. We can come back at 2 p.m. So that you're a bit refreshed, stretch your legs, and get ready for the next session, next few notebooks.
Actually, return to noon, 12 p.m. Mountain. It's because Anirudh is located
yeah.
Anirudh is located in Toronto. That's why he said 2 p.m., but it's actually 12 p.m. It should be in about like 5 minutes.
I'm 2 hours ahead, so that's the confusion. Okay, I'll see you.
All right, everyone, we're back. Now we're gonna go pass the word to Anirudh, our lead instructor, who will cover the last classes of our content.
Okay, I'll share my screen now. Okay, so you all should be able to see my screen here. So thanks, Taras, for giving that great session. I learned few things that even I didn't know. I hope you all learned something as well. So now that you actually, so let me actually open this. So now that you have actually gone through all these notebooks, what you'll see next is actually you'll actually have to apply all the skills that you have learned till now in the next few notebooks. So we'll start with pipelines. So basically, you'll start using all the concepts you learned before: imputers, filling in missing values, turning categorical data using one-hot encoding. In a high level, you won't actually go into depth in one of those concepts, but here you'll actually be using different components, stitch them together to create something called a pipeline. So that's what we'll start with here. So what are pipelines? So before going through this, I'll just explain it in a very simple way. So you have different steps when you create a model, right from processing the data, cleaning it, filling in missing values, converting categorical data to one-hot encoding, and then finally applying the model and then getting your predictions. So if you can think of all these different steps as different components, pipeline is nothing but it combines all these steps into one coherent single workflow that makes it easier to read your code, organize your code much better. And you might ask, what's the point of organizing code if it actually doesn't improve my predictions? So when you actually have more complex tasks and when you want to deploy these models into production, and what I mean by that is create applications out of it and send them into, let's say, some kind of a end user application, like detecting the sentiment, or in this case, predicting the house prices. You want your code to be readable so that you can manage it very well. It's actually, you'll start losing track of what your code is doing in different pieces if you don't have a cleaner code. And trust me, I have actually experienced this quite sometimes. You might actually become unclear on the code that you yourself have written. So that's why we are actually looking at these pipelines. That's what's written here. So cleaner code, fewer bugs, easier to productionize. It's basically a better way to keep track and enhance your code in terms of readability. So in the first step here, you just read the data, split it into the test, the train and validation sets, and then you check through the first 5 rows. And then now, what's the actual pipeline step here? So that's what we will be seeing here. So you see, you have actually seen simple imputer before. So this is basically used to let me put this on the side. Okay, so this simple imputer is basically used to impute the values or fill in the missing values, and then also the categorical data transformations. So again, filling in the values, turning them into one-hot encoding. You're just bundling those two into one single pipeline. And then finally, you actually need to define something called a column transformer. So this column transformer is nothing but, you see here, it takes in the numerical transformer, which is nothing but filling in the missing values for your numerical data, and the categorical transformer, which has 2 steps inside. So filling in the missing categorical data and then one-hot encoding them. So you just combine both those steps in one single pipeline called pre-processor. Next step would be to define your model. I'm sure you've seen this a couple of times. You just define the class random forest regressor, and then you define the model. Now you have two components, preprocessor and model. You take these two and combine them into one single pipeline. That's your actual pipeline, which just takes in the data, does all the pre-processing steps, passes the data to the model, trains the model on that data set, and then does a prediction as well. So this preprocessor, if you see, is actually made up of a bunch of more low-level components that you're actually stitching together to make a higher level component in the bigger pipeline. So I've just run through it very quickly, and now we'll actually go into the actual notebook. So I hope you can see the notebook on screen. So, okay. So here, what we'll be doing is just as before, we'll just set up the notebook and make sure the notebook starts and all the paths to the data sets in your working directory are set. Once that is done, we'll actually get into using the pipelines. So the first step is exactly the same. It's always going to be the same. You read the input data as a pandas data frame, and then you take the target, the column that you're actually trying to predict, and you basically drop it from your training set and save it in a variable called y, which is basically your training target. You use train test split to basically split the data, and then now here, what you're trying to do is you're trying to select those columns only which have less than 10 values. So cardinality is actually the number of unique values in the column. So to be able to actually understand this better, the best way to always, what you can do is always open a new code cell, just take the code that you're trying to understand. So I'm actually unsure of what's going on here. So I'm just going to take that, paste it here, and I'm going to see, oh, I haven't actually run this, right? Okay. So I would like to know what's actually going on in this step. So I just took that code, copied it here, and I see that they're actually gathering all the names of every column in the data set. Next step is to check for n unique. So n unique is a function. It's an inbuilt function of pandas data frame that just checks for the number of unique items in that particular column. So let's actually take one of them. So I'm going to take basement finish as F1, and I'm just going to see X green full. So this is the column I'm trying to count. I guess, okay, I actually need a column of type object. Let me see. You don't actually need to do this. I'm just showing you, if you don't understand something, this is the best way to actually do it. Let me see. Okay, building type. Building type sounds like a categorical feature to me. So I'm going to see, yes. So this is a categorical feature. It's of type object. So I need to count the number of unique values in this. So I'm going to say n unique. And what I'm actually going to get is the count of the number of unique values in that particular feature or column, which is 5. 5 is actually less than 10. So this is going to get added in this variable. So you can delete this anyway. So that's what's going on here. You're just selecting the columns or features which have unique values of number less than 10 out of type object. Similarly, for numerical columns, I'm doing the same thing. We're just going to separate out the numerical features by identifying them of type int64 or float64. Now let's actually see what's the xtrain here. So the xtrain dot head here is just giving me the first 5 rows. You see, these are the first 5 rows that I have, and these are all the numerical values and categorical values combined. So you can actually immediately see there are missing values. There either I do a simple imputation or just drop them. You've actually seen techniques to actually fill in missing values before. So now, instead of doing them manually step by step, we're going to define components, as I mentioned before, that are part of a bigger pipeline that you would be running. So as a first step, I would use a simple imputer to basically fill in the missing values of pre-processing the numerical data and then pre-processing the categorical data. So this is my only step for numerical dealing with numerical data. And these are my 2 steps inside my pipeline to deal with categorical data. So you can start to observe how this looks much better, how it's easier to read stuff rather than writing them down individually step by step. So all you need to do is deal with these higher level functions. And this concept of pipelines is actually called abstraction. You're basically hiding the unnecessary details and only showing what is necessary. Now you have this column transformer, which I showed you before, which is combining both these steps together. So here I have my numerical transformer ready to go and my categorical transformer. And then as a last step, I have to define my model and then combine both of them in one single pipeline. All I need to do is do a dot fit so that you can treat the pipeline as a model. It's just that it has more steps inside. So that's why you see the same function dot fit and dot predict that you would have used if you were using it directly on the model. Let's run this code. It's basically taking the data is going through all these transformers, and then finally the mean absolute error is 17,861. So now I hope you understood this step, because this is what pipeline is all about. It's bringing together different components and putting together in one single step. Okay. I'm just going to check if there are any questions. Okay. So now it's actually our chance to define the simple imputer and so on. So as a first step, what we are going to do is define our pre-processing step. So the goal of this exercise is to actually do something different than what has been done here. So in this case, you can see the simple imputer strategy is just constant. We can use multiple different things and not just that single type of filling in value. So I'm going to take the simple imputer. And so the quickest way to check for documentation in these notebooks is to use Shift Tab. So you just do Shift Tab and you're going to actually see the documentation pop up. Here, what you can do is understand the different strategies. So the strategy we used before in the previous cell was constant. So that means it replaces missing values with fill value. So you need to define another parameter called fill value that you see here. And when you use a strategy called constant, it's just going to fill in those missing values with that dummy number or value or whatever it is. I'm going to try and use, let's say, median. So replace missing values with median along with each column. So there's no one right approach. Mean is not the best approach. Median is not the best approach. You actually need to try out multiple things and then run your model, get the MAE, and then see which is giving you a lesser result. Sometimes it might be more of depending on your own data. So let's say it's the year value. So let's say we have a column called year and it has all the years 2012, 2013, 1996, and so on. It doesn't make sense for me to replace the missing value with average year. There's no such thing as 2013.567 year. Like, it doesn't make sense. So in that case, maybe I can use median or most frequent, because I need the year to be a 4-digit number, integer exactly as is. It cannot be float. So that's how you think about these things. So for now, I'm just going to use strategy median. And then we need to define the categorical transformer. So categorical transformer actually has two steps inside. One is filling in the missing values, but the second step is to actually encode them, one-hot encode them, and there are multiple encoding techniques. We are using one-hot encoder here. So for that, you actually need a pipeline. So I'm going to say pipeline, and then I'm going to say steps. How do I know it's actually steps? You just check the documentation, plain and simple. So you can even see the way they implemented it here in the documentation itself. You need to say pipeline, and then they didn't say steps, but I'm explicitly defining that I'm declaring a parameter called steps in this function. So my first step will be to fill in the missing values. So I'm going to name it whatever I want. I can actually even name it with my own name. Yes, it doesn't matter. But for the sake of readability and so that other people can understand it better, I'm going to say imputer. And this imputer is nothing but the same simple imputer that you used before. Let's see what has been used before. So it says most frequent. Okay, let's actually use the same strategy most frequent. This is the first step. Now the second step is to define my one hot encoding. So I'm going to actually say one hot encode, and then I have my one hot encoder defined here. I can use the same one here that they've used, handle unknown ignore. You can actually, again, you can actually read about each individual one by just clicking Shift Tab and seeing what happens when you say handle unknown as ignore. So that's what you can see here. Now I have my two components defined, a numerical transformer and a categorical transformer. And then we've bundled them both into one more pipeline called column transformer. So this is the one that actually does the transformation step. It goes through each column and then it applies these steps individually. Finally, I need to define my model. So my model is the random forest model. And I can say n estimators. So we can say 100 for now. It doesn't really matter. And then random state as 0. So one important thing to point out here is that this random state actually changes the way Kaggle expects your answers. So random state is basically meant for reproducibility. So what I mean by that is these models, the weights of these models are always initialized randomly. So all these models, there are multiple different parameters within the model and hyperparameters. The weights of the model. The weights of the model initially, you don't know what they are. So either you can set them all as 0 or you can initialize them randomly. You need a random number generator to actually initialize, get those random values. This random state is actually the seed value for that random number generator. You can actually read more about it. I'm just not going into depth right now, but what I'm trying to tell you is the random state defines reproducibility. If I actually change the random state, you might still get a good answer, but Kaggle might actually expect something else because their random state is different. That's the purpose of this. And commonly, you'll actually see random state being initialized to 42 in a couple of articles. There's actually a reason for that. If any of you have read the book Hitchhiker's Guide to Galaxy, they mention that's the answer to everything in the universe. That's where it comes from. Okay, so now we got that right. Next, go to the next cell. So in the next cell, basically, I'm going to take my preprocessor that I have defined here, my model that I have defined here, and bundle them into one more pipeline. And then all I'm going to do is pipeline.fit, xtrain, ytrain, predict, and then get the mean absolute error. So that's what's going to happen here. So when I ran this code, the data is actually going through the preprocessor. So xtrain is actually going through simple imputer. It's going through these two steps, and it's going through the model. It is getting fit, and you're actually doing a prediction here. And finally you're getting the score. A good exercise for you is to actually even bundle these two steps. So why don't you actually define another function, and in that function you can actually have dot fit and dot predict and put it in the pipeline. So your pipeline, the moment you say you run the pipeline, you might as well just execute all the steps. We are not doing that here, but it's a good exercise for you. Now we need to actually get the test set predictions. So for that, I need to actually know what my test set variable is called. It's called xtest. So that's what I'm going to do here. I'm going to generate the predictions. So to generate the predictions, I actually need to use my pipeline here. So my pipeline, you see, it's actually so simple. I don't need to worry about processing my test set and then replace the missing values, one hot encode them. Actually, I'm not worried about any of those steps. I know that my pipeline actually has everything combined into one single module. So all I need to do is say predict on the xtest, and that's it. So your predictions, you can actually check your predictions. So preds test, you can see all your predictions right here. You didn't have to actually worry about any of the previous steps, although each step has further steps, further computations within them. When you are at this point, all you are worried about is, do I have my test data set or not? That's the simplicity of pipelines. Okay. Okay, the video is lagging. I see. So can you hear me well now, or it's still lagging? Okay, I'm assuming that my video is fine for now. Okay, so I hope you understood the concept I was trying to tell you, pipelines, which is just a way of gathering all your different components and combining it into one. Okay, video is choppy. Okay, that's fine. Okay, I guess we have to move on from here. But anyway, I hope you understood why we need pipelines here. It's just a good way to have clean code. And now finally, as you did before, you can create a submission.csv. You'll see that submission.csv come up here, and then you can submit your results. So I'm just going to pause here for a few seconds to see if you have any questions on the pipelines exercise we did. This is this is a very useful and it's not a necessary step, but it's a useful step. That's the difference. Cleaning your data and encoding your data are necessary steps. Pipeline is not a necessary step, it's a useful step. That's the main difference. Now, if there are no more questions, I will go on to cross-validation. So you have your model, let's say you train your model on a good amount of data, and then finally you see that you have to evaluate your model. So your evaluation criteria here is the mean absolute error, MAE, and you see that you have a very good score. Your model is actually doing well on your validation data, and then finally you start trying to test it on real data, and you see your model is actually failing. Why? You just tested your model to the best extent possible, and you see it's doing well. So why isn't it actually doing so well on real-time test data or data that you actually get in production? The reason is maybe you haven't tested it very well enough. So let's say you have 5,000 rows and you use 1,000 rows, the last 1,000 rows to actually use as your validation dataset. Somehow, luckily, maybe it turns out that your model might actually do very well just on those particular 1,000 rows, and it doesn't do well on anything else. That's the issue over there. So how do you actually make sure to test better? Maybe I'm going to use 4,000 rows for testing. I might not be lucky enough to have 4,000 good data points, but there is an issue here. You just reduce your training data set to 1,000 rows, which is not at all enough, and your model will do bad. So we need a way to somehow test on a much larger data set, but at the same time, you need a good amount of data for training. That is where cross validation actually comes in, and this is very important. If you are actually working as a data scientist or plan to work as a data scientist, this is very key. If you actually talk about this during your interview, they'll actually know you actually know how to test your models really rigorously. Cross validation is one such method. So forget the text and just focus on this image right here. This is the best explanation for cross validation. So imagine your data set, imagine this whole block here is your full data set. You split it into chunks or folds. So that is where the term k-fold cross-validation comes in. So you have these different folds of your big data set, and you dedicate 4 of those folds for training, 1 of those folds for testing. This is exactly the same as if you didn't have any of these other ones. So this is what you normally do. In cross-validation, what happens is you keep shifting the validation block step by step. So for the second round of experimentation, instead of using this block of data, these first 1,000 rows of data for validating, you use the next 1,000 rows. So from 2,000 to 3,000, you use that set as your validation, and the rest of it, 1,000 to 2,000 and 3,000 to 5,000, you use that as training. And you see the block keeps moving forward. In this way, you are effectively utilizing the whole data for training and testing without without having any overfitting or data leakage or any other kind of a thing. So that's where this is what cross validation is all about. So for the first experiment, you get certain accuracy. For the second experiment, you get some other accuracy. Third, fourth, fifth, sixth. You just average out everything to get the accuracy as a whole. So you have effectively trained on the whole data without actually worrying about the insufficient data. So that's what is being explained here. We use the first fold as validation. This gives us a measure of the accuracy. Next, we hold out data from the second fold and then estimate it again, and so on. So when should you use cross-validation and when should you not? For me personally, I would just use it all the time. It just makes it better. But if you have a data set that's too huge, cross-validation actually takes a very long time, because each time you have to fit your model, train it, test it, and again you have to keep fitting your model, which is computationally very expensive. And these are all free. Kaggle is obviously providing free notebooks for you. But when you start working in a company, or if you are already working, most companies deal with compute provided by cloud providers like Microsoft Azure or Google Cloud or Amazon. There your compute gets charged per hour. So per hour, you're spending $1 or $2 or something to even run your code or use the notebook. So imagine spending 12 hours on cross-validation on a huge data set. You've literally actually cost your company certain dollars, which you could have avoided if you just not use cross-validation. So that's the real impact of using and not using cross-validation in an industry scenario. If you have a large data set, because it's large enough, you have a good amount of training data, good amount of validation data, you don't need to use anything. But if it's a small data set, you can just as well use cross-validation because it doesn't take too much time. So that is the whole explanation about cross-validation, and that's what we're going to do here. So we are actually going to use pipelines that you've learned before. You're going to use the pipeline, and then finally, sklearn provides a simple way to implement cross-validation. I would suggest as a good practice, before using this, implement cross-validation from scratch on your own. Don't use any libraries. Look at this image, read through the documentation and just try to implement cross-validation from scratch using for loops and whatever technique you want. You'll understand it much better, and then you can start using cross-val score directly off the shelf. This is the best way to practice coding, or machine learning or anything. Implement them from scratch and then start using the higher level modules. So now you have defined your cross-val score. CV is nothing but the number of folds. So each of these blocks is one fold. So here we have defined 5 folds. So you have 5 blocks. One of those blocks is validation. And you see for each experiment, you have one MAE, and you finally take a mean of all those things to get the last score. That's what they've done here. All the scores, take the mean, and this is your average MAE score across all the folds. So this is cross-validation. If you have any questions, I'll pause here. If not, we can go over the actual notebook. If I'm going too fast or too slow, let me know, but yeah. Okay. Can you please explain the difference between overfitting and underfitting? Okay, that's a good point. So imagine you, okay, this is how I'll explain it. Somebody, Jaya has just asked a question, what is overfitting and underfitting? So let's say you are actually preparing for a test. How do you prepare for it? Let's say I'm going to study all the material, look at the past papers, and start preparing. So when you overfit, what happens is you prepared so well, you actually aced all your practice tests, you're doing so well on your test. The moment I give you a new question that you have not seen before, you instantly fail. You actually don't know what to do. That's overfitting. You've done so well on your validation and your training and your practice tests, but you're unable to do well on something new. This is overfitting. You've actually overfit on your existing data. Underfitting is the opposite. You're not even able to understand your own textbook. You're not able to perform well on your own practice test, let alone ace an actual exam. This is underfitting. So overfitting is basically going too much into your own data and not doing well on another exam. Underfitting is forget the exam. You're not actually able to do anything on your practice tests. This is a simplistic way to explain it. In terms of modeling, overfitting actually means a model has high variance. So if your model is too complex, if you have a neural network with billions of parameters, or if you have some kind of a decision tree or any other model that actually is so complex that it's trying to fit every data point in your training data, that has high variance, it's bad. It won't actually perform very well. Underfitting is something like models that have high sort of like low bias. Not low bias, sorry, high bias. So linear regression. If you know about the model linear regression, it's just a straight line. Y equal to mx plus c. It's that equation. It's just a straight line. The model is so biased that it will always try to fit a straight line no matter the shape of the data. If your data is very curvy, it still tries to fit a straight line as best as possible. It's highly biased in its thinking. So it will not fit very well even on your own training data. This is underfitting. I hope you understood it. The next question is, so when you're so well fitted on your training data that you fail on new, yes. So yeah, you're so well fitted on your training data that new data is, the model is not actually able to do that. So the model has high variance, meaning that a slight change in the data, a slight change in the parameters is impacting it tenfold. That's overfitting and underfitting. So there is actually a nice, let me show this to you. There is actually a nice diagram to illustrate this, which makes it very clear. Let me show you. There is a dots, right? there is, yeah, this is what I was looking for. Okay. So let me show this to you quickly. I'll move on. Okay, I hope you can see this image. So basically, it's like throwing darts. So this is the ground truth. If you start throwing darts, a model which has high bias and low variance doesn't even go anywhere near the ground truth. It goes way far from that. A model with low bias and low variance is very good. Obviously, that's an ideal one, but low bias means it doesn't necessarily have any biases like linear regression, but at the same time, it's not as complicated as a neural network. So you actually hit the bullseye. In case of overfitting, which is low bias and high variance, you see that I've actually practiced darts for, let's say, all my life. And finally, I go to this sports bar and I try to throw something. I'm actually throwing it all around the dartboard. This is overfitting. I'm not able to cope up with the new environment, and then high variance. So this is a good illustration to really understand overfitting and underfitting. So, okay, let's move on now. Again, we have to set up our notebook and run this one. So this is exactly the same as before. You're getting the data and then you're dropping the sale price, and then finally you're taking the numerical data. For now, we are sticking with numerical data alone. I'm going to wait until this comes. Feel free to ask more questions. More questions will actually help you actually maybe point out something I may have missed. That's the purpose. Okay, so you see, this is a standard procedure, and by now this should be done even by closing your eyes. So I just got the data and I am viewing the data here. I got all the numerical values only. You see, I don't actually have any categorical data. So now I'm going to use a very simple pipeline. Because I have numerical data only, all I need is a simple imputer to fill in the missing values and a random forest regressor to actually do my modeling work. So I've defined my pipeline with these steps. Now I'm going to do cross-validation. So visualizing cross-validation with those 5 folds is very important, because here all you see is just one single cross-val and nothing else. So that's what's going on here. Now what we'll actually do is we will actually, so I hope you understood until now this is what cross-validation is doing. But as a first step in this exercise, what you need to do is you need to write a function that goes over all the different possible ways of setting the parameter for the random forest. So you see here, random forest, it actually has a hyperparameter called n estimators. There's a difference between parameters and hyperparameters. You can look it up, but essentially this thing that you see here, this thing n estimators, it's actually a hyperparameter. It's not a parameter of random forest. What we are trying to do in this function here is try out different possibilities. Here, by default, they've initialized it with the value 50. It could be 100, 150, 200, 250, 300, all the way until 1000, 10,000, and so on. We need a way to systematically experiment through all these different values. That's the whole purpose of this function. So begin by writing the function that reports the average MAE, that takes in the data, creates the folds, creates the pipeline, and then finally gives you a score. So whenever I run this function, I just need to get the score. That's it. So that's what we're going to do. So first step is I need a pipeline. So I'm going to define my pipeline here with the steps. You can code along with me. It's useful to do that. Never copy paste. It's better to write. First step is I'm going to, I just need the preprocessor and then the model. That's what I'm going to do. Process data. Simple imputer. And my next step is the actual model. So here what I'm actually going to do is The whole purpose of this getScore function is to try out different possibilities, experiment different estimator values. So how do you actually do that? So whenever you see these things in a function, these quotations, 3 triple quotes, triple double quotes, this is actually a documentation. In this documentation, let's say I have no clue what n estimators is. So I'm going to read the documentation. It says the number of trees in the forest. So I'm going to just take this as is, just to avoid spelling mistakes, and put it here. Now what's going to happen is, each time I run that function, I'm actually going to create a new model, a completely different model than before, which has a different value of n estimators. Now I need to actually do cross-val scoring. So score -1. I'll take my cross-val function, and what do I need to do here? I need my estimator. So what's my estimator here? It's my pipeline. So my pipeline is the estimator, and I need my x and y. So what are my x and y? I need to get them from here. So x is nothing but x and y is the target. So that is what I'll have here. It's here, x comma y. And then finally you need the actual scoring strategy. How do you want to score? The cross-val is just a framework, but internally you need some kind of a scoring mechanism, and that I'm going to take it from here to avoid spelling mistakes. I'm not done yet. I actually have my score, but as you know, cross-val score is going to give me, in this case, they're asking me to do it over 3 folds. So I'm going to get 3 different MAE values. I need to take a mean of all of them. So I'm just going to say final score is score.mean. Now, because it's a function, I need to actually return the value. So I'm going to do return final score, and let me just run this. Incorrect. Yeah, this is the reason why I was copy pasting, to avoid spelling mistakes. All right. Okay. I got an error. I know how to solve this, but can somebody in the audience tell me why I got this error? I just explained this concept in the previous one, and I even referred a book, Hitchhiker's Guide to Galaxy, for this. We can solve this error with just one parameter. If somebody can answer it, you can feel free to answer it in the chat. It's a very simple solution to this. I'll wait for a second. My code is not wrong. There is actually nothing wrong with my code. It's actually correct and it's running fine. I'm still getting an MAE, which is the purpose, but I'm getting the wrong MAE according to Kaggle. Kaggle, yes, random state. So that's the whole reason. So random state is meant for reproducibility. Now you actually see the importance of random state. So you see, now I got it correct because I put random state of 0, which is what Kaggle asks you to do. I hope that's clear. Now let's actually move on to the next step. And this is a bit tricky. So now you actually need to run this getScore function a couple of times. How many times? That's what they wrote here. You need to run the same code again and again for n estimators equal to 50, 100, 150, all the way until 400. You need to read through this carefully. Store your results in a Python dictionary where results of I is the average MAE returned by getScore of I. I here is referring to these values, 50, 100, 150, 300, and so on. This is how I'm going to do it. So first of all, how do I create this sequence? Before going into that step, I'm going to, let's say, a rough work. So first thing is I need to produce this sequence before even jumping to the function. The best way in Python to produce that sequence is using the range function. So for I in range, how do I define my range? I know it's from 50 to 400. So I'm going to say 50. I'm going to define my range, 401. There's a reason I specifically said 401 and not 400, because the range function goes until but the last one. So it goes all up until 400, but it doesn't touch 401. But there is a mistake with this. If I run this, I'm actually going to get an interval of 1. I need to define the interval as well. So as another parameter, I just need to say 50 here. So I'm actually going to get this. So now that I've figured out how to actually create my sequence, let's go ahead and create a dictionary out of this. So how do I create a dictionary? So I'm going to use dictionary comprehension and just going to remove these ones and put I. So you see, this is actually a dictionary now. Here, you're actually going to do get score. So this is what you actually need to do. So you need to actually create this dictionary is what they are exactly asking you to do. So you need to say 50 and then call the function get underscore score with the value 50 and then 100 and then 150, 200 and all the way under 400. So that's what I'm going to do. I'm just going to leave it here. So let's do that. So I'm going to say I and get score of I for I in range of 50 to 401 in steps of 50. So basically it's going to take a time because each time it's calling get score, the whole pipeline is being initialized, random forest is being initialized, a new estimator is being set, cross validation, which is another huge time taking task, is executing. It's taking the mean and it's getting back the value. So this will definitely take some time. This is the computational complexity of cross validation. While it executes, you can ask me any question you have. We just need to wait. We can't do much here. Okay, I see that it actually ran. So let me, okay, now let's actually see how results looks like to get a better picture. So you see here for I actually ran it. I ran the function get score of 50. It went through all these steps and gave me an MAE of final score of 18,353 and so on. So basically it's yeah, each value is there now. Finally, you see that I can actually see the MAE is decreasing well. So increasing the estimators did help me. That's what I knew. So now that's basically what I showed you in plain code. They're actually visualizing it for you. So you see, as I increase the number of estimators, it actually went and oh, I might have not noticed this. So you see the MAE actually dropped to a minimum at 200 and then it went up. So out of these, the best MAE is actually at 200 because it's an absolute error. The lower the error, the better. Now you need to answer the question. Okay, so the N estimator best is nothing but 200 here because that's where I can visualize clearly it's dropping low. So that's the correct answer. And as I mentioned, hyperparameter tuning is something completely different. What we did here is definitely hyperparameter tuning, but we just tuned one parameter. There are multiple different parameters. There is a nice functionality called grid search CV that scikit-learn provides that allows you to basically create a grid of parameters. So I'll show you one example. So you see here, they actually have a grid of parameters. And then you go through every possible hyperparameter and you get the best one. This is even more computationally complex than cross-validation. So when you want to use it, be sure to have everything correct before you run the code. I hope that is clear. We are going to get to the last section, which is XGBoost. I'm sure most of you have heard it. People in Kaggle who attend competitions go crazy over using XGBoost in every one of their notebooks. Now we're going to check gradient boosting. So before So this paragraph explains gradient boosting. Given the time, I'm actually not going to go over all this. I'm going to explain something that you need to know before you go over XGBoost. So you need to understand the concept of gradient boosting. The X in gradient XGBoost actually comes from the speed. It's called extreme gradient boosting. It just adds speed and performance to the existing algorithm, but the core technique is called gradient boosting. For that, again, I'm going to use this picture here. So for this problem, we can use simple linear regression, but here you guys are running. Can you explain what are the issues with? Okay, somebody has a question that says we are using random forest regressor. What's the issue with linear regression? So actually, you can try linear regression, and you can. There's nothing wrong with trying linear regression. Maybe linear regression turns out it's better than random forest, but you don't know that unless you actually build the model and see the performance. So in general, as a data scientist, you actually need to use multiple different models, compare their performance, and see the output. One practical business related reason of why people stick to random forest in linear regression is because of the explainability. When you present your model to the business, to the client, they don't have any clue of machine learning. They don't know what's going on. And when they see the predictions, they need to know why did the model give this prediction for this input. Linear regression and random forest provide a way to explain your outputs. For this particular input, your model has actually predicted, your model has actually used this particular feature, has weighted, has given more importance to these features rather than these features. This kind of an explainability gives confidence to business owners, gives confidence to clients that you're not actually doing some weird stuff behind, you're actually doing something very logical and practical. That's the reason. Last question is, are we not doing the data leakage notebook? Because we are crunching on time, I'm just going to go over what that concept is. It's a notebook that you don't actually have to execute code. It's actually it's sort of like an article you have to actually read through, but I'm just going to touch upon it slightly. So yeah, gradient boosting is an algorithm where you actually need to, so the concept of gradient boosting is you take a bunch of weak learners, very weak machine learning algorithms. So weak in the sense they have an accuracy of less than 50%. You take a bunch of them, pool all them together, and you make a learner which is much stronger than anyone individually. That's the purpose of weak learners, a gradient boosting. So what gradient boosting actually does is it takes, so you start here. So it takes your training data and your target, it trains the model, it does some prediction. All that is fine. Now, the core idea of gradient boosting is to actually take the error. So you see, you've actually predicted y1 prime, y1 hat, and then you have y1, you get the error. Let's say your house price is $1,000, you predicted 1,500. Error is 500. You capture that error, store it in a variable, and then train a new model which learns to predict the error. It's no longer predicting the target, it's actually predicting your error. That's what's happening here. You take the residuals, these are called residuals, that's why the variable r. So you take the residuals, you train a new model. That can be any model. It can be a random forest, it can be a linear regression, it can be anything. It can be a neural network also. You take that model, you train it, but this time you train the same data on predicting the error, and then you get new errors. You take that residuals, again you start predicting more. You keep predicting more and more errors, and finally you take all these different trees and you add them up. So this is your original model, which is actually predicting the house price, but these models are actually predicting your residuals. You take your original model, sum it up with all these models, and finally you get your gradient boosted tree. Now, what's the purpose of actually training it on error? What's happening? So when you take your original model, and let's say you predicted your actual prediction is your ground truth is $1,000, but you predicted 1,500. You as a human know the error is 500 because you just subtracted both of them. What if the model can foresee the error itself? What if the model can actually go ahead and predict what is the actual error and then subtract it directly before it gives the final prediction? So let's say it predicted 1,500 and it also predicted the error would be 300, let's say. Your final answer would actually be 1500 minus 300, which is 1200. So you see how the model is actually doing better now than before. It is able to predict the error and the output and combining both of them to do something much better. This is the explanation I have for gradient boosting. If you understood this concept, that's all you need to know. When you're free, go over this quickly to understand it better. I'm going to go over the notebook. I hope gradient boosting is clear, and that is what it means. Residuals are nothing but the errors, your error, your prediction versus your final output. Sorry, your ground truth versus your final output. That's residual. I'm going to go over this notebook a bit quickly. So we need to get an XGBoost regressor. It's still running. Okay, so basically here you need to get your XGBoost regressor, and it's exactly the same. You just need to get the model, run it through your code, get the predictions, and see your answers. That's what's going on. So the model is aware of, it's not aware of its own error, it's predicting the error. So in this picture, if you see, it's being trained, I'll zoom in a little bit. So it's actually being trained on the residuals. It's learning to predict the error. It doesn't actually know what the error is. It's estimating the error, hopefully that it will help it in doing better predictions. That is what's going on, to answer your question, Sai. Okay, I'm going to go over this. So we need XGBoost regressor here. And then I'm going to do dot fit train. Okay, random state. So once you do that, you need to get your predictions. So my model dot predict it's valid, and you get the answer. So then finally you get the mean absolute error, which is nothing but y valid, and then predictions underscore 1. So you finally, it's the exact same thing. It's just you're using XGBoost to do the same thing that you do again and again, just improving your model with estimators and so on. So I'm actually going to stop here to give Talis some time, but hopefully you understood XGBoost, how it works. All these exercises are nothing but using the same model again and again to use different parameters. Before I stop, I'm just going to quickly mention what is that whole data leakage thing all about. So imagine that, let's say you are preparing for an exam, you are going to give the exam, and then let's say you actually have, I'm going to stop sharing my screen. Let's say you actually have the test answers directly with you when you're writing the test. Obviously, you will ace the exam because I have the question paper, but I also have the answers with me. I can actually clearly get 100% score in the exam because I can just look at the answer and write it. This is data leakage. If the model somehow by mistake you have fed the sale price as well as one of the feature, the model is able to look ahead. It actually can throw away all the features and it can just look at that one final answer, which is the actual ground truth, and just replace it. My model could be simply copy pasting the answer from the data. That's the whole concept of data leakage. I would encourage you to go through this notebook and read through it. Talis, over to you. I think that's all.
Thank you, Anirudh, so much. And this was very valuable information. I hope everyone got a chance to learn a little bit, or learn a lot actually, from the lessons from Anirudh. And yeah, let me just remind everyone that we are running a raffle for Chromecast Mini. So this is the last call to fill out the survey and RSVP to Intro to Deep Learning in order to get into the raffle. And in the meantime, I'm just talk about some other stuff that's going on. In the end of all the sessions of the study jam, we will have an extra raffle if you complete all of them. So this will be for a Google Home Mini. So if you want to participate in this raffle, make sure to complete all the levels. So when this is over, I invite everyone to finalize the notebooks at your own pace, go back to the tutorials, go back to the exercise, read them all, read through the documentations of the libraries, and try to join the competition as the notebook suggests. I think that's the best way to learn these methods and try to tune your model until you get a nice score. And if at any point you're stuck or confused, feel free to use our Discord channel to post your questions, and we'll be around to help you. And also make sure to register for the next session to learn a bit about deep learning soon. We also invite everyone to volunteer with us if you are interested. We are a chapter composed of volunteers. They are passionate about cloud, about machine learning, and much more. So if you want to be a part of this, please fill out this form that I believe Anya will share in the chat for us. And also I invite everyone to join the Google ML community network. If you are interested in connecting to other communities that are also passionate about machine learning, please take a look at it and see the details and the form to join it as well. So lastly, let's go to the raffle. Let me just make sure that I don't have any new names on it. I believe we're good to go. So I believe I'll just give 1 more minute in order to make sure that everyone who wants to join the raffle has a chance to do so.
Hey, Thales, just wait a couple of minutes. I see some folks have filled in the survey. I will update the wheel of names. Thank you.
Okay, perfect. Thank you so much. Oh, okay. I see some people missing in the raffle. We'll make sure to add everyone who's eligible to the raffle. This wheel of names will be updated shortly. Is there an age limitation on on becoming a volunteer? I believe there is not. I will have to. Someone else will have to confirm it, but I don't think there is. Okay, let me just reshare the survey link. This is the survey link. Oh, okay. But I believe there is no age limitation on becoming a volunteer, but we'll have to, I would have to confirm it with the other organizers. Just go back to raffle slides while you're waiting. So this is what is up. We are doing a raffle for everyone has filled out the survey and has RSVP'd to the next section. So to join the raffle, you'll just have to fill out the survey and you have to RSVP to the next session. So the next session link is okay. Vanya just copied it into the chat, so this is where you have to RSVP on. Yes, I can definitely do so. Let me grab the link for you. Oh, there is a problem with the volunteer link. I believe we can share a new form in the Discord channel once that is figured out. Yeah, I apologize about that. Go back to Raffle. Okay, in the meantime, you can send an email to the email address that Vanya just posted in the chat. All right, I haven't updated names. So, all right, I believe that is enough time. So let's see who wins the Chromecast Mini today. All right, so Sai Sidish, you got the Chromecast Mini. So congratulations, the organization team will contact you about how they will deliver to you your prize.
Saib, please send me a DM with your email and home mail address to send you the prize. Thanks for your participation.
All right, so with that, we cover everything that we wanted to share today in our study jam. So thank you everyone for participating. Thank you for being part of this. Hope everyone had a chance to learn something, to share your experiences. And I see everyone in the next session, which is about intro to deep learning.
Thanks, everyone.
Yeah, thank you, Anirudh. It was a great session.